Welcome back, everyone. Let's get right into it, shall we? Today, we are tackling an explainer on a topic that honestly haunts a lot of trainees: astigmatic refractive error and the conoid of Sturm. My promise to you is that by the end of this session, you aren't just going to memorize this for your OCAP exams, your written boards. You are going to intuitively master the physics, the anatomy, and the clinical reasoning so that this entire concept becomes completely second nature.
Here's our clinical roadmap for today's session. We'll start by defining astigmatic eye error, move on to the conoid of Sturm, tackle the circle of least confusion, look at calculating spherical equivalent, and wrap up with collapsing the conoid.
Section 1. Astigmatic eye error defined. We're going to really understand what excess converging power actually means.
You know, up to this point in your optics training, you've probably been looking at lenses in total isolation. But let's look at the physical reality of a living human eye. And here is a classic board trap for you, so definitely pay attention here. Do not confuse absolute lens power with eye error. When we say an eye has an error of +1 diopter or +2 diopters in a specific meridian, we aren't saying the eye only has 1 or 2 diopters of total power. No way. We're talking about the amount of excess converging power, beyond what's actually needed to put parallel rays of light perfectly onto the retina.
To really grasp this, we need a baseline, right? So here is a massive OCAP pearl. Goulstrand's reduced schematic eye has exactly 60 diopters of total converging power. You've got to lock that number into your memory. 60 diopters. That is what a normal, perfectly emmetropic eye uses to bend light directly onto the fovea.
All right, let's do a little active recall. Picture a patient sitting right there in your exam chair. If their eye has a +1 diopter error in the vertical meridian and a +2 diopter error in the horizontal meridian, where exactly do the focal lines land inside their eye? I'll give you a second. Try to mentally calculate those focal distances.
Okay, let's break down the math behind the anatomy here. Our horizontal meridian has +2 diopters of excess error. If we add that to our 60 diopter baseline, we get a total power of 62 diopters, right? To find the focal distance, we simply divide 1 by 62, and that gives us an anterior focal line located exactly 16.1 millimeters behind the cornea. Meanwhile, the vertical meridian has +1 diopter of error, giving us 61 diopters total. 1 divided by 61 places our posterior focal line at 16.4 millimeters. Now, considering an average eye is about 24 millimeters long, this beautifully illustrates that both of these focal lines are just floating right there in the middle of the vitreous cavity.
Section 2. The conoid of Sturm. We'll be tracing the actual path of light.
And this brings us perfectly to the anatomical phenomenon created by these floating focal lines. This is absolutely mandatory board vocabulary, the conoid of Sturm. Named after a 17th century mathematician, Johann Christoph Sturm, it's defined simply as the three-dimensional space from one focal line to the other. I really want you to visualize this. It's like a trumpet-shaped tunnel of light spanning that tiny 0.3 millimeter gap between the 16.1 millimeter mark and the 16.4 millimeter mark in the vitreous space. Clinically speaking, when a patient complains of ghosting or shadowing around letters on the Snellen chart, well, they're describing the visual artifact of this exact 3D space landing imprecisely on their macula.
Section 3. Circle of least confusion. Finding the most point-like focus. So, if we take a cross-section of this conoid, we find a very specific spot that has the absolute highest clinical importance for optimizing your patient's visual acuity. We call this the circle of least confusion. Inside the conoid of Sturm, the light is constantly changing shape, right? It goes from a horizontal oval to a circle to a vertical oval. The circle of least confusion is the exact cross-section where the incoming light is the most focused. It's literally the most point-like spot in the entire conoid.
Which leads us to a core clinical dogma in ophthalmology. The smaller the circle of least confusion, the better the vision. This right here is your anchor point for spherical correction. But listen closely to the phrasing. It's the least confusion. It's still a circle, not a true pinpoint of light. Which means vision here is better, sure, but fundamentally, it's still suboptimal.
Section 4. Calculating spherical equivalent. Finding the mathematical center. So how exactly do we manipulate this conoid? Let's shift into some clinical reasoning and find the mathematical center of our patient's refractive error. Time for some more retrieval practice. Going back to our example eye, what is the spherical equivalent of an eye with a +1 diopter error and a +2 diopter error? Take a sec and mentally calculate that average.
Got it? Yep, it's +1.50 diopters. The average of +1 and +2 is simply +1.50.
This number perfectly represents the mathematical center of our eye's error.
Now for the actual clinical application. If the eye's error spherical equivalent is plus 1.50 diopters, what spherical lens do you need to pull from your trial lens case to move that circle of least confusion precisely onto the retina? Think about it. Just flip the sign in your head.
You're going to need a minus 1.50 diopter spherical lens. The absolutely crucial point here is understanding what this lens physically does. Putting a minus 1.50 lens in front of the eye physically shifts the entire conoid structure backward. It essentially drags that circle of least confusion right out of the vitreous cavity and drops it smack onto the fovea. If you're only allowed to use a spherical lens, this gives the patient the best possible vision.
Section 5. Collapsing the conoid. Achieving 20/20 vision.
But listen, as attending physicians, we do not settle for least confusion. We want perfection. And here is a super common board trap. Moving the circle of least confusion to the retina is not the ultimate goal. Why? Well, because the image is still a blurry circle. If we wish to truly optimize vision, we must utterly collapse the conoid of Sturm entirely onto the retina. We have to force those two separate focal lines back into a single razor-sharp focal point.
Let's break down the step-by-step clinical algorithm for how we actually pull this off. Step 1. You identify the cylindrical error in each meridian. Step 2. You select a corrective cylinder of the exact opposite sign to offset that error. And Step 3. You combine those corrective cylinders into a single spherocylindrical lens. This, my friends, is exactly what collapses the conoid.
Let's see how this builds using our trusty example eye. In the vertical meridian at axis 180, remember we had a plus 1.00 diopter error. To fix that, we need a minus 1.00 diopter corrective lens at axis 180. In the horizontal meridian at axis 090, we had a plus 2.00 diopter error. We simply offset that with a minus 2.00 diopter corrective lens at axis 090. Here is your next big O-capped pearl. The corrective lenses are always equal in power but opposite in sign to the spherocylindrical error lenses.
When we combine those two theoretical corrective cylinders, what do we get? A standard glasses prescription. Negative 1.00, negative 1.00, axes 090. Or if you're writing it in plus cylinder format, negative 2.00 plus 1.00, axes 180. And just look at how the math works out. The spherical equivalent of our corrective prescription is negative 1.50, which perfectly offsets the eye's average error of plus 1.50. It's beautiful, really. The math and the anatomy align perfectly.
All right, let's run a rapid-fire board review to really cement your pattern recognition strategies here. If the eye has an error of -2 at axis 90 and +1 at axis 180, your corrective lenses are exactly the opposite, +2 at 90 and -1 at 180. What if the eye's error is +4 at 90 and -1.5 at 180? Well, your correction is simply -4 at 90 and +1.5 at 180. Every single error cylinder demands an exact corrective opposite to collapse that condoid down into a single, sharp point on the fovea. So, we've covered the normal anatomy, the physical optics, and the exact step-by-step algorithm to collapse the conoid of Sturm. Let me leave you with this provocative question. Now that you truly intuitively understand the physics of what is happening inside the vitreous cavity, are you ready to actually refract an astigmatic eye in the clinic? Because with this mental framework, you are more than ready to tackle your next chapter. Keep studying hard, and I'll see you in the next explainer.